Okay, everybody, this is my Exam 1 Essay 2 video. This is actually take 2. I accidentally deleted the other video that I just made. So, we're going to try this again. First off, we're going to talk about resting membrane potential, the different conditions and factors that affect our resting membrane potential. Okay, so we're going to start off, let's erase this really quick. Little teaser there. Okay, so right here we have a cell. Okay, and in our cell, we have different types of ions. We have different types inside, we have different types outside. And they're at different concentrations, right? So we know potassium ions and negatively charged proteins are going to be higher inside the cell than they are outside the cell. And we know sodium chloride and calcium ions are going to be higher outside the cell than they are going to be inside the cell, okay? So that's the first factor we got to consider when we're determining resting membrane potential, is our concentrations. And with our concentrations, we got to remember the gradients. Where are those ions going to want to flow? Are they going to want to flow inside the cell or outside the cell, based on where the high concentration is and where the low concentration is, okay? So our potassium and our proteins, those are higher inside the cell. So it's a high concentration in, low concentration out. Therefore, those ions are going to want to flow outside the cell, right? Remember when we touched up on osmosis, we kind of briefly talked about this. The high concentrations, we're going to go down the mountain to the low concentration, okay? So potassium, protein, they're going to want to go outside the cell, okay? And then our sodium, chloride, and calcium ions are higher outside the cell, therefore they're going to flow down the mountain inside the cell. That's where they're going to want to go. That's their gradient. It's their chemical gradient. We got to remember chemical gradient, okay? The next thing we got to consider is our permeability. Is the cell permeable to those ions? Is it going to let them flow in? Are they even going to be able to get in or out of the cell? Okay. So with that, we have different channels and gated channels around our cell membrane. Okay. So we have things like potassium leak channels here, voltage gated sodium channels, voltage gated potassium channels, voltage gated calcium and chloride channels. We also have things like mechanically gated and ligand-gated sodium channels, or even just cation channels. So there's lots of different channels and transporters around our cell membrane, okay? That are going to let specific ions in or out, right? But notice, we're going to mainly just focus on those channels that I just mentioned. And notice the only one that's going to be open all of the time is our potassium leak channel. Okay, that's the only channel that's open 100% of the time. No matter what, it's always open. Okay, so then we consider, so we have that. So we know that the cell is very permeable to potassium. Okay, because that channel is always open. So let's go to the gradient. Okay, you know, because we have a high concentration inside the cell and a low concentration outside the cell, our potassium is going to want to flow out of the cell. Okay. So I think we're good there. So because our cell is most permeable to potassium, it's going to have the highest effect on our resting membrane potential. All these other ions will have some effect. They'll leak in there when they can, but not a lot. Potassium is our main contributor to resting membrane potential, okay? And so what that's going to do is when potassium is leaving our cell, remember, we can't just bring in just a bunch of, we can't just bring in a bunch of positive ion or potassium charges. You can't just put just positives into the cell. It's always going to have this negative partner with it, okay? So just imagine when we put, say, potassium chloride into the cell, our potassium has negative partners, okay? We can't have an accumulation of a charge, but we can have a separation of charge. That's what's going to happen here, is potassium, with all of its positive charges, is going to leave the cell, and it's going to leave behind all of its negative partners because they can't get through. Okay, they're not going to be able to get through the channels, okay? So we're going to leave behind all of these negative charges. We're going to have a bunch of these positive charges on the outside that are attracted to those negative charges. Okay? So remember, potassium leaves behind all of its negative buddies, leaves them inside the cell, okay? And all of our positive charges are leaving. So we're having more negatives than we are positives now because of this. Now, essentially what resting membrane potential is, or how it's determined. Not, okay, this is a lie. It's not how it's determined, but it's a good way to think about it. Is if you were a dude, you're just standing in the middle of the cell, you look up at the ceiling, at the cell membrane, you're going to see all these charges on it. Okay, so you count them up. So in this case, we're going to have 70 of them. Okay, and then you determine what kind of charges are they and how many of them are there. So remember, all of our potassium that left, or not all of it, but it's starting to leaving behind its negative partners inside the cell. So we're going to see more negatively charges on the inside of the cell membrane. So therefore, it's going to be a negative 70 millivolts. Okay, so that's the gist of how our resting membrane potential is determined. Now let's look at it from a mathematical equation. This is our Nernst equation up here. Ex equals negative 61.5 divided by Z times the log of the concentration inside and the concentration outside the cell. So mainly what's determined with our Nernst equation is if we were to plug just one specific ion into this equation, what is its effect going to be on the cell membrane? Or essentially, if it was just that ion and that ion alone, this is what the resting membrane potential would be, okay? So Z, that's our valence charge. So let's use potassium first. Or we're going to use potassium and sodium for this example. So both of their valence charge is going to be a +1, okay? And so look at our equation. We're going to do all of our math. We'll start with potassium. Potassium's higher inside than it's outside. I can't remember the exact concentrations for potassium, but essentially our Nernst equation for potassium is going to be right around negative 90 millivolts. Okay, and if we were to do it for sodium, our Nernst equation for sodium also going to be, or not also, but it's going to be right around a positive 20 millivolts. Okay, so we can see that our negative 90 is closer to our negative 70, which means, and we already knew this based off the concept we drew out here, our potassium has the highest effect on our resting membrane potential, or it's the one that determines most of what our resting membrane potential is. It's the highest shareholder, another way to look at it, if you're in econ or business, whatever. Okay, and also based off this equation, we can kind of guess what effect is going to have it based on these variables. Okay, so remember, our concentrations are going to have some effect on it. Charge is going to have some effect on it as well, on the magnitude of our resting membrane potential, or at least the membrane potential of that ion. Okay, so now let's move over here, because we know we can't just do one ion. There's multiple ions that have effect on the cell membrane, right? Our potassium is the only one that's very permeable to the cell. But these other ions are still kind of leaking in, having some effect on it. So then we have our Goldman's equation, which is our membrane voltage is equal to essentially the first part of our Nernst equation, but now we're considering all of the ions, not just potassium or not just one, okay? All of them. So we're going to have a log of our concentration of sodium in plus concentration of potassium inside plus our chloride concentration outside of the cell divided by our concentration of sodium outside plus our potassium concentration outside plus our chloride concentration inside, okay? We could also throw calcium and proteins on there too, but we're just going to mainly use these three for this equation, okay? So we plug all of our concentrations in. We're going to put a +1 for our charge here, and that brings us to our membrane voltage of negative 70 millivolts. Okay, which is our resting membrane potential. So that's how we determined our resting membrane potential. Let's do that, okay? Now, one last thing we have to consider too is what's called driving force. Now, what driving force is essentially how much that ion is going to want to move, okay? So like sodium has a very high driving force. If you let it, it would just shoot right into the cell. It really, really, really wants to go into the cell. Potassium, not as much. So the higher the driving force, the more that thing is going to want to move inside the cell or outside the cell. But it's just how much that ion wants to move. Okay, our driving force is determined by our membrane voltage minus our Nernst equation for that ion, okay? So let's see. So we can kind of practice with this and plug in a little bit. So we're going to use, let's do sodium. Let's actually do potassium. Okay, so let's set up our equation. Driving force is equal to -70 minus our -90, which is going to equal a positive 20. Okay, so now we can look at this and see, okay, it wants to get in 20. All right, that's our number. But then we can also look at the charge here. So we have, it's going to be a positive number, and our potassium ion has a positive charge. So because that, it's going to want to repel, because positives repel each other. It's going to want to repel itself out of the cell, okay? Via a number of 20, how powerful that is or whatever, okay? And that's essentially the gist of resting membrane potential. Just remember all the different things that contribute to resting membrane potential: concentration, gradients, permeability, all of our channels here. Remember, our potassium leak is always open. Therefore, it's most permeable to potassium. Potassium has the highest effect on our resting membrane potential. And then remember our Nernst equation, the ins and outs of that, driving force, and our Goldman's equation. Okay, so let me stop the video for a brief moment, and we'll get set up for part 2 of this video.